Hello and welcome everyone. We all know water is absolutely essential, but what's the science that makes it safe enough to drink or pure enough for heavy industry? Well, that's what we're diving into today. This is a deep dive into water technology based on the fantastic material prepared by Dr. Arun Kumar P, and it's designed specifically to help you, the students of CMS College of Engineering and Technology, absolutely nail your exams. Think of this as your complete study guide. We're going to walk through all the core principles and processes you need to know, transforming raw water into one of our planet's most vital resources. So grab your notes and let's get into it.
All right, here's our game plan. We've got 5 major sections. We'll start with the basics, water quality parameters. Then we'll look at how cities purify our water and how we can make salt water drinkable. And finally, we'll get into the heavy-duty world of industrial boilers. First the problems, and then, of course, the solutions.
Okay, first things first. Before we can even think about treating water, we need to know how to talk about it. We need a shared language to describe its quality. And trust me, understanding these basic parameters is the foundation for everything else we're going to cover. So let's start with the stuff you can notice right away, what you can see, smell, or taste. For drinking water, colors should be super low, less than 5 units. Any weird tastes or odors? That could be a sign of anything from treatment chemicals to something decaying in the water. And then there's turbidity. That's just a fancy word for cloudiness. That also has a strict limit of less than 5 NTU. Next up, pH. You've probably heard of this one. It's simply a measure of how acidic or alkaline the water is. It's a scale from 0 to 14. Right in the middle, 7 is neutral. Anything below that is acidic, and anything above that is alkaline or basic. And here's a number you'll definitely want to remember for your exam. For the water we drink to be safe, we're aiming for a very specific sweet spot, a pH between 6.5 and 8.5. This is super important because it makes sure the water isn't corrosive and won't cause other issues. Okay, moving beyond pH, there are 2 other big chemical parameters. First is alkalinity. Now, this isn't just about pH, it's about the water's ability to resist changes in pH, to neutralize acids. Then you have TDS, or total dissolved solids. This is basically a measure of all the stuff dissolved in the water. And for drinking water, the magic number is less than 500 parts per million. All right, this next one is a classic point of confusion, so let's clear it up. BOD versus COD. They both measure pollution, but they do it in really different ways. BOD, biological oxygen demand, uses actual bacteria to see how much oxygen they consume breaking down organic waste. The key here? It only measures biologically decomposable stuff, and it takes 5 whole days. COD, on the other hand, uses strong chemicals to measure everything that can be oxidized, and it's way faster, only about 3 hours. So COD gives you a bigger, quicker picture of the total pollution. And what about hard water? You've all experienced this. It's when you just can't get your soap to lather up properly. Well, the reason for that comes down to chemistry. It's caused by dissolved salts, specifically from 2 culprits, calcium and magnesium ions. So now that we have the language to describe water quality, how do we actually improve it for an entire city? Let's follow the water's journey from a source like a river through a whole lot of treatment all the way to the faucet in your home. It's basically a 6-step process. We start by getting the big junk out with screening and aeration, and we end with the most important step for our health, sterilization. Let's walk through it. The first few steps are all about getting rid of the obvious physical stuff. Screening is just what it sounds like, running the water through screens to catch leaves, sticks, whatever. Then aeration mixes the water with air to get rid of nasty tastes and smells. Sedimentation lets heavy stuff like sand just sink to the bottom naturally. But what about the tiny, fine particles? For that, we use coagulation. We add a chemical like alum that makes all those tiny particles stick together in clumps so they're big enough to remove. After those clumps have formed, the water moves on to filtration. A lot of times, this is done with a big sand filter, just like the one you see here. The water flows down through all these different layers: fine sand, coarse sand, gravel. That top layer of fine sand is really the workhorse. It traps all the leftover particles and even a lot of bacteria. And that brings us to the final, and I mean the absolute most critical step for public health: sterilization or disinfection. The water might look perfectly clean by now, but it could still be teeming with invisible, dangerous germs. This last stage is all about killing those harmful pathogens to make the water truly, completely safe to drink. Now, a really important concept in sterilization is something called breakpoint chlorination. It can be a little tricky, so follow me here. When you first add chlorine, it gets used up fighting all the impurities in the water. As you add more, the amount of chlorine left over, the residual, starts to go up. But then it does something weird. It drops. You have to add enough chlorine to push past that drop, past that break point. Only then do you get what's called free residual chlorine, and that's the stuff that stays in the water, keeping it safe all the way through the pipes to your house.
But what happens if you don't have a river nearby? What if all you have is the ocean? Well, that's where desalination comes in. We're going to look at the main technology used today to turn salt water into fresh water: reverse osmosis.
So, to understand reverse osmosis, you first have to understand regular osmosis. It's a basic law of nature. Imagine you have salt water on one side of a special filter and fresh water on the other. Nature wants to balance things out, so the fresh water will actually move towards the salt water to try and dilute it. That natural push is called osmotic pressure.
So, reverse osmosis is all about fighting that natural tendency. What we do is apply a whole lot of mechanical pressure to the saltwater side, way more pressure than the natural osmotic pressure. This forces the water molecules to go the opposite way they want to. The pure water gets squeezed through the filter, leaving all the salt and other junk behind. Pretty clever, right?
Okay, let's switch gears completely now. We're moving from the water you drink to the water that powers our industries. And for all you future engineers at CMX College of Engineering and Technology, pay close attention. This is where using the wrong kind of water goes from being a small problem to an absolute nightmare.
Just look at how incredibly strict the rules are for water going into an industrial boiler. Hardness has to be less than 0.2 parts per million, that's basically zero. And dissolved oxygen, absolutely none allowed. These aren't just suggestions. If you ignore these limits, you're asking for huge problems like corrosion, scale, and even dangerous failures. Okay, here's another key comparison you need to know: sludge versus scale. When you have hard water in a boiler, it creates one of these two things. Sludge is that loose, slimy gunk. It's bad for efficiency, but you can usually clean it out. Scale? Scale is the real enemy. It's a hard, rock-like coating that bakes right onto the metal. It's way more dangerous, wastes a ton of fuel, and can even cause the boiler to explode. And if you need proof of how bad scale is, just look at these numbers. A layer of scale, not even a millimeter thick, can waste 15% of your fuel. Get up to just 1.25 millimeters, and you're wasting half your fuel. It's an absolute economic and engineering disaster. You're basically just paying to heat up the scale instead of the water. Here's another nasty problem with a scary-sounding name: caustic embrittlement. This is what happens when the water chemistry creates a highly corrosive substance inside the boiler. This stuff seeps into tiny cracks in the metal, especially around joints, and literally makes the steel brittle and weak. This can lead to a sudden, catastrophic failure. And then there's just straight-up corrosion, the boiler literally rusting from the inside out. There are three main culprits. Dissolved oxygen is a big one, especially at high temperatures. Dissolved CO2 forms an acid that eats away at the metal. And some salts can even break down and form incredibly aggressive hydrochloric acid inside your boiler. Whew, we've talked about a lot of pretty serious problems: scale, sludge, corrosion. So how do we actually fight back? Well, this final section is all about the solutions, the clever ways engineers condition and treat water to prevent all those bad things from happening. There are really two main strategies here. You have external conditioning, which is a proactive approach. You treat the water and remove all the bad stuff before it even gets into the boiler. Then you have internal conditioning, which is more reactive. You add chemicals directly into the boiler to deal with any impurities that might still be in there. The best, most complete external treatment is called ion exchange or demineralization. It's a two-step process. First, the hard water goes through a resin that grabs all the positive ions, like calcium and magnesium, and swaps them for hydrogen ions. Then, the water goes through a second resin that grabs all the negative ions, like sulfates and chlorides, and swaps them for hydroxide ions. And what do you get when you combine a hydrogen ion and a hydroxide ion? You get pure H2O. The result is incredibly pure water. Now, it's really important to know the difference between this modern demineralization process and the older zeolite method. The zeolite process just swaps the hardness ions for sodium ions, so it makes the water soft, but it leaves a bunch of sodium salts dissolved in it. Demineralization is far more powerful. It takes out everything, both positive and negative ions, giving you water that's almost completely pure, which is exactly what modern high-pressure boilers need.
So what happens if a little bit of hardness still gets through? Well, that's where your internal conditioning methods come in as a last line of defense. You can add phosphates to turn any remaining hardness into a soft sludge that's easy to remove. Or you can use something called Calgon, which cleverly grabs onto calcium ions and stops them from ever forming scale in the first place. There are other methods too that either coat the particles so they can't stick or trap them in a gel.
So there you have it, from the basic chemistry of a glass of water all the way to the complex systems that power our industries. But I want to leave you with one final question to think about. We've talked about drinking water and boilers, but think bigger. What's an emerging field of engineering, maybe in electronics, green energy, or even space travel, where the ability to create ultra-pure water is going to be absolutely essential? Something to think about.